Maximum Product Subarray. Here's a question that separates the good from the great. Maximum Product Subarray looks easy, until you hit those negative numbers and zeros. This Pattern Mastery 100 staple pops up at companies like Google and Amazon, and it's famous for tripping up even seasoned coders. If you can nail this one, you'll show interviewers that you're not just following patterns, you truly understand array dynamics and edge case thinking. Let's unlock the secret together. Let's break down the challenge. Given an integer array, your job is to find the contiguous subarray that has the largest product. Unlike some problems, multiplying negatives can flip the result, and zeros reset your progress. That's why this problem is sneakier than it seems. Now let's assess our options. A brute force approach would try every subarray and compute the product, on squared or worse, but we want on time. The trick is to keep track of both the maximum and minimum products ending at each index, because a negative number could turn your lowest product into the new maximum if multiplied. As we scan, we update both, and always check for zeros that reset the product chain. Here's the structure of our solution. First, initialize three variables. Max_prod for the global max. Cur_max for the current maximum product ending here. Cur_min for the current minimum, for handling negatives. Then, start all at the first element. Next, for each number in the array, starting from index 1. If the number is negative, swap current maximum and current minimum. Update current maximum as the higher of the number itself or number times current maximum. Update current minimum as the lower of the number itself or number times current minimum. Update maximum product if current maximum is greater. And lastly, return maximum product.
Let's try to implement it using solution 1. We begin by defining the solution class. This is the container that holds our method. Then we declare the maxProduct method. It takes an array of integers and returns the maximum product of any contiguous subarray. Next, we store the length of the array in n. This makes the code cleaner and easier to read. We create two arrays. MaxedP at index I will hold the maximum product ending at position I. MindP at index I will hold the minimum product ending at position I. We track both because a negative number can turn a very small product into a very large one. We initialize the first position in both arrays with the first number in nums. Any subarray that ends at index 0 is just that single value. Then we set res to the first number. At this point, the best product we have seen so far is simply the first element. After that, we start a loop from index 1 to the end of the array. Each index is processed exactly once, so this runs in linear time. Here we check whether the current number is non-negative. If it is, multiplying it does not flip the sign of our running products. For the new maximum product ending at the current index, we choose between two options. Option 1, start fresh with the current number. Option 2, extend the previous maximum product by multiplying it with the current number. We take whichever option gives a larger product. For the minimum product at the current index, we choose the smaller value between the current number and the previous minimum multiplied by the current number. Now we handle the case where the current number is negative. This is where things get interesting. A negative value flips signs, so the maximum and minimum roles can swap. Here we compute the new maximum product using the previous minimum. A negative times a negative can produce a large positive value, which might be our best product so far, and we compute the new minimum using the previous maximum. A positive multiplied by a negative becomes negative, which can be the new smallest product. This closes the conditional logic. At this point, we have updated both the maximum and minimum products for the current index. Next, we compare the current maximum product with our global result. If the current maximum is larger than res, we update res. That means we have found a better subarray product. This closes the loop. By now, every index in the array has been considered as an ending point for a subarray. And finally, we return res. This is the maximum product across all contiguous subarrays. And that is how this algorithm works. It sets up arrays to track both maximum and minimum running products, updates them at each position depending on the sign of the current number, and keeps a global result that captures the largest product found in the entire array. Efficient, simple, and elegant. Check. This test verifies the maximum product subarray solution. The challenge is to handle negative values correctly, because they can flip the sign of a product. The array contains the values 2, 3, -2, and 4. We track both a running maximum product and a running minimum product, because multiplying by a negative number can turn a small negative value into a new maximum. Start with the first value, 2. The current maximum is 2. The current minimum is also 2. Next value is 3. Both products stay positive. 2 times 3 equals 6. So the current maximum becomes 6. Next value is -2. Because this value is negative, the sign flips. The best product we have seen so far remains 6. Next value is 4. None of the possible products at this step exceed 6. So the highest product found in any contiguous subarray is 2 times 3, which equals 6. The output is 6, matching the expected 6. The algorithm correctly identifies the maximum product subarray, even when negative values are present. Now let's try another implement approach using solution 2. We begin with the solution class. This is simply the container holding our optimized method. Then we declare the max product method. It takes an array of integers and returns the largest product of any contiguous subarray. Next, we initialize 3 values. Curmax stores the maximum product ending at the current position. Curmin stores the minimum product ending at the current position. Res stores the global maximum product found so far. All 3 begin at the first number, since every subarray must include at least one element. After that, we start looping through the remaining numbers one by one. This loop touches each index once, giving us linear time. Inside the loop, we store the current number in X for easy reference. Next, we check whether the current number is negative. A negative value can flip the sign of our running products, meaning the previous minimum might suddenly become the new maximum. So if X is negative, we swap curmax and curmin. This ensures the sign change is handled correctly. Then we update the running maximum product. We choose between starting a new subarray at X, or extending the previous curmax by multiplying it with X. Next, we update the running minimum product. We choose between X itself, or extending the previous curmin by multiplying it with X. This is important because the minimum can become the maximum later if we multiply by another negative number. After that, we compare curmax with our global result. If curmax is larger, we update res. That ends the loop. By this point, we have tracked the best product ending at every index, while adapting to sign flips efficiently. And finally, we return res, the largest product of any contiguous subarray. And that is how this algorithm works. It keeps a running maximum and minimum product, swaps them when a negative number appears, and updates the global best as it scans the array. Efficient, simple, and elegant. Check. This test checks how the maximum product subarray solution handles zeros and negative numbers. The array contains the values -2, 0, and -1. Because multiplying by 0 resets the product, we must carefully track both the current maximum and minimum products as we scan. Step-by-step analysis. Start with -2. Current maximum is -2. Current minimum is -2. Best so far is -2. Next value is 0. Any product that includes 0 becomes 0. So the current maximum becomes 0. The current minimum also becomes 0. 0 is greater than -2. So the best so far becomes 0. Next value is -1. We consider starting fresh with -1, or extending with 0 times -1, which is 0. The best product we can get at this point is still 0. So the global best stays 0. With a 0 in the middle, no contiguous subarray produces a product greater than 0. The output is 0, matching the expected 0. The implementation correctly handles sign flips and 0 resets.
Let's have a quick recap. Breakdown recap. This problem challenges us to find the contiguous subarray that produces the largest product. What makes it tricky is that negatives and zeros completely change the game. One negative can flip a loss into a win, while a 0 can reset everything. The task is less about simple multiplication and more about managing unpredictable swings in sign and value. Assess recap. We started by comparing approaches. A brute force method that checks every subarray is too slow to scale. The key insight is recognizing that a negative number can turn a previous minimum into a new maximum. By keeping track of both the current max and min at each step, we can handle those sign flips dynamically and efficiently in a single pass. Structure recap. Our logic revolves around 3 values: the global maximum product, the current maximum, and the current minimum. As we move through the array, if we hit a negative, we swap the current max and min before updating them. Each new number becomes a decision point. Do we start over or multiply to extend the existing chain? Implement recap. When we implemented the logic, the process flowed smoothly. At every step, We updated our running max and min products, handled sign reversals, and kept a record of the global maximum as it evolved. Conceptually, it felt like walking through the array with real-time recalibration, adjusting to every twist caused by negatives and zeros. Check recap. Testing confirmed the approach works perfectly. In our example, the product chain resets correctly at 0 and captures the best possible result. 2. Even with more complex inputs, the algorithm consistently identifies the strongest contiguous product in ON time and constant space. The big takeaway here is adaptability. The maximum product subarray teaches you that in algorithmic thinking, just like in problem solving, your approach must adjust to changing conditions. It's not just about finding the maximum. It's about managing uncertainty efficiently and confidently.